Okay, we'll get started today with assignment 1. And we actually looked at the first 4 exercises of assignment 1 in a previous lecture. So there's a record of that in a video format if you want to review that. We can also go over those problems again today for a second time if we have time and if you're interested in doing that. But what I'd like to do now is just jump right to exercise 5. I believe we did exercise 4. Is that correct? But we did not do exercise 5. All right. And so let's take a look at that. This is a single statement in C++. All statements are terminated with semicolons. There's the semicolon. And this statement is comprised of many sub-expressions. And one of the things that you need to do as you think through all of these problems is how to evaluate the sub-expressions in a statement in the right order. So when you see this, you see operators here. This is the output operator. There's 3 occurrences of the output operator. So one of the things you need to decide is which one goes first, which one goes second, and so on. And when an operator or a function call is evaluated, what is the result of that? So that's the so we're going to review those concepts and the skills that you need to think through these problems. All right, I'm just going to bring up Notepad. We're not going to do any programming on these problems. In the quiz, which you will take a week from today. So on February 15th, we have a quiz, and the quiz will look very much like a long list of these little problems that you work out on paper. So we'll look at these exercises in the same way that you would see them and work them out in that quiz format. So if we look at this statement right here, we've got 3 operators. They're all the same type of operator. So what we do is we do left to right order of execution. And most operators are done in a left to right order. There's a few exceptions, but they're rare. And I'm not going to get into that. So the first thing that we do is, and let me copy this over here. Actually, let's just do like this. Let's work our way through this, evaluating each sub-expression. So the first sub-expression to evaluate actually is this one right here. We need to take 1 and divide it by 2. And remember, there's 2 kinds of division, and they both have the same symbol. You know one versus the other based on whether the operands are both integers or not. Here the operands, which are 1 and 2, are both integers, and therefore the compiler interprets that slash as integer division. So it'll generate machine instructions that execute integer division here. And when this sub-expression evaluates, you can think of it as being replaced by its result. And the result of taking 1 and dividing by 2 is 0. So we replace 1/2 with a 0. That's how you can. That's one mental abstraction that you can use to compute the results of this code as if it were running in a computer. So 1 divided by 2 would be replaced by a 0. It's evaluated to 0, and then that 0 becomes the right-hand operand of this operator, and the left-hand operand is cout. So we're passing 0 into cout. We're passing 0 into the output operator, and so that gets printed. 0 gets printed here. And actually, we don't print the space. We just print the 0. So that's the result. First we evaluated this sub-expression. That became an input to the next sub-expression. Now this sub-expression is also replaced by what it evaluates to. And what does that sub-expression evaluate to? What do we replace? What I have highlighted there, what would we replace that with to carry on with our simulated execution of this program? Anybody know? What does that expression evaluate to? No? I know somebody knows this. You're just not saying it. I'll believe that. It's replaced by cout. The output operator, when the output operator runs, it returns, it evaluates to this argument that appears on the left-hand side. So we pass something out, and if we passed, x out into there, it would evaluate to x out. And it does that just for convenience. Because this evaluates to cout, that means we can chain these output operations. Look at this. Replace that mentally with cout. That then becomes the left-hand side of this next operator. So this is the literal string. It's a string that started and ended with quotes. And this becomes the argument, the next argument that's evaluated along with the cout that this returns. Those are the two arguments that are then passed into this second instance of the output operator. So we print this. So comma and a space. So now that this sub-expression has been evaluated, right, what does this evaluate to? What does this sub-expression get replaced by at this point? I know you know this one. Cout, right? Because just the second instance of the output operator running. This also evaluates to cout. So that's the left-hand side of this last output operator. And the right-hand side is this. Oh, we're kind of jumping around here. We need to do this first. We need to do this division before we evaluate the results of this operator. So here we see 1 divided by 2.0. Well, the 0.0 makes that a floating point value. The compiler looks at the slash and says that's floating point division. And so I generate machine code that results in 0.5 rather than 0 that we just saw in the integer division form. So this is 0.5. That's the right-hand side of this operator. The left-hand side of the operator is cout. So we're going to print 0.5. Maybe it prints 0.5. We're not going to worry about that on the quiz. You don't have to worry about that. And now this whole, the execution of this here, sorry, not copy, but the execution of this last operator, the evaluation of that last operator results in cout. So you can think of this whole expression as being replaced by cout. But we don't do anything with it. So it's of no consequence. So we're not concerned with that. Any questions on this? Exercise 5. What about 6? Anyway, this is the answer. This is what you would write on your quiz paper. Let's look at exercise 6. And there are 3 lines of code here. 3 statements. Each statement is terminated by a semicolon. When the above code runs, what does it output to the console? So similar to the last exercise, we want to write down what will appear in the console when the program runs. So when you look at something like this, you can look at it as a picture and take a snapshot of the whole thing and get a feeling for what it's all about. You can say, oh, there's 3 lines there, 3 sentences. But what you're going to need to do is you're going to need to shift into sequential thinking mode and look at each piece of the code, one little piece at a time, and figure out what that piece does. All right? And we would start with the first line, the first statement. And in here, when I look at that, I see 2 activities. And you should see 2 activities. Let me show you something that has 1 activity. If we did this, I would see something that has 1 activity. It says allocate storage for an integer and let it be known by I. That's 1 activity. Now, what's in the storage is random. We don't know what's in there. And that's the purpose of the second activity. After allocating the storage, let's initialize that storage to a value, 0, or 2 in the case of the problem we're evaluating. So those are the 2 activities that you should think about or be aware of when you see this type of a statement. You're declaring a variable, or defining. You're defining a variable. Declaring a variable, by the way, says a variable exists. And defining a variable is an instruction to the compiler to generate machine instructions that allocates memory for the storage of that variable. And so we create a variable I and initialize it to 0. Now, here's a trick. You could just make a mental note and say, well, I is 2. And let's think now. Well, there's 2 things. One is reading through the code and sort of analyzing it, thinking about what it does. And the other way to process the code is to actually pretend you're the computer and execute it. And let's do 2 passes through this code. Let's do 1 pass where we try to understand what the pieces are, what they do, and then we'll go back and we'll do a second pass through the code where we simulate the execution of the program. So we've just talked about the first line. What about the second line here? And once again, you'll have to look at this and how many activities are there in there? Well, I see 4. There's the definition of K, the allocation of memory, an integer. There's the assignment to that storage, to that value. There's an assignment to K based on the results of this sub-expression. So when this sub-expression is evaluated, what it evaluates to is then assigned into K. So defining K is 1 activity. Assigning something to K is a second activity. And now, how many activities are involved in evaluating the sub-expression? Well, there's an increment operator, and then there's multiplication. So there's 2 activities there. So I count 4 activities. Now, how do these things, how do these work? What is the sequence in which we can sort of evaluate the result of this line of code? Well, allocate K, create a K. First thing we do. And although it doesn't have to be the first thing, we could evaluate this, then create the K, and then assign into it. We could do it like that. I'll do it like this. Let's create K, but we cannot assign K anything yet, because we need to evaluate the sub-expression. So let's evaluate this sub-expression. We've got two operators. We have the post increment operator. That's what that's called, post increment. This operator down here, it looks similar, except it's in front of the variable. That's called the pre-increment operator. We've got a post increment operator, and we've got multiplication. Which one runs first? I'll give you a hint. The word post means it's delayed. Multiplication runs first. And after the sub-expression in which the increment operator appears in, after that sub-expression is evaluated, then the increment occurs. All right, let's look at the third, of course, and then after the increment occurs, then the result of this sub-expression is assigned in the k. Let's look at the third line. Well, we have an output operator here, but it has C out on the left-hand side and this sub-expression on the right-hand side. So we're not going to be able to evaluate that operator until we evaluate the sub-expression. And the reason is that all of the operations inside the sub-expression have higher precedence than the output operator. The output operator has a low precedence relative to the other operators that appear in the expression. It's just like in math. You know, in math you would have something like 2 plus 3 times 4. When you see that, do you get 24 or do you get 20? What would be the right answer if you were a math teacher on a, huh? A 14? Yes. Oh, sorry. I would fail that one. So 14, because look, even though the plus sign comes first, you do the multiplication first, because multiplication has higher precedence. So there's that concept of order of operation. So when we look at this, we have to decide, well, what gets done first? And well, we see a multiplication and we see an addition here, so we just remembered from math that we do multiplication first, and that's the same here in computer code. So the addition operation is delayed. We're going to do multiplication first. Now the multiplication involves this right-hand operand, 2, and a left-hand operand. Is it just I or is it plus plus I? Well, that's plus plus I, that means increment I. And that's a pre-increment operator. So we have to decide, do we increment I first and then multiply by 2? Or do we multiply by 2 and then increment I? No, if it was the post increment, in other words, the plus plus followed I, we would multiply by 2 first. But it's the pre-increment operator. So we increment I first, then we use the result in that multiplication. The pre-increment operator has very high precedence. So that means the first thing that we would do is this. This would be evaluated, whatever I is. If I were 14, when we run this, when we evaluate this operation, I would become 15. And then we would multiply by 2 to get 30, and then we would add k to get 33, or whatever k is, and then we would print the 33. So that would be the sequence of operations. Okay, so now we looked at each line and we tried to remember and recall and all the rules that we need to, and the meaning of the symbols that we need to carry out our simulated execution now. So let's go back, we'll start again, and pretend that we're the computer and run the program. We define I, initialize it to 2. So I'm going to make a little note. I mean, you could make a mental note, but rather than risk forgetting, I'm going to make a written note that there's an I, and it is currently equal to 2. All right, let's do the next line. Well, we talked about this already, that we do the multiplication I times 2 first, and when that's done, then we increment I. So I times 2. I times 2 gives us 4. And actually the 4 is now assigned into K. So K is 4. We don't increment I. Yeah, I mean, if we increment I before assigning to K, it's okay. It doesn't affect K anyway. So we have a K, and we assign 4 to it. And now we increment I. See, it's good to write things down so you don't forget where you're at. So this post increment, remember the post increment is delayed until the sub-expression is evaluated. And actually you can think of it as before it's evaluated and used. And we just do the sub-expression at the end when it's done. I mean the post increment. All right, let's do the last line. This increment operator, the pre-increment operator, has the highest precedence, so we're going to need to increment I. Well, if you were smart enough to make a mental note, your mental I would be equal to 3, and you make it a 4. But if your memory is not so good, then you'll go to your written record and see that, oh, I is 3. I need to increment I. That becomes 4. And now I'll use I in this expression, I times 2. So I times 2 becomes 4 times 2, which is 8. You know what? Well, we have to make a mental note that that sub-expression has been evaluated to 8. In fact, let's do it like this. I'm going to show you an easier way to do this, hopefully. Let's go ahead and copy this thing here. Let's do it like this. We need to increment I. I was 3, and now I becomes 4. Plus I evaluates to 4. Now we have 4 times 2. This evaluates to 8. And K is 4. We have a written record of that. And then this addition can now be evaluated. This is 12. Now 12 is sent to C out. That means we print 12. So the answer that you write down on your quiz paper would be 12. And this is scratch work. You want to make sure that we see the answer. That's what's printed, 12. We don't print C out, arrow 12, although you can have it as your temporary sort of a work area. All right, let's take a look at the next one. Write a C++ program that computes the sum of integers 0 through n, where n is an integer entered by the user. And actually, I'm not, I don't expect you to write a C++ program with completely correct syntax. So it can be in a pseudo code format, is fine with me. We need to compute the sum of integers 0 through n, where n is an integer entered by the user. So we declare an n, we input it from the standard input stream. That's a standard code, we've used that many times. And then we need to add together the values 0 through n. Now the standard approach is to define some kind of an accumulator. You set it to 0, and then look at each value 0 through n and add it into this accumulator, this sum, the sum variable. So you need a loop that's going to run, that's going to take an index I, start at 0, and run it up through n. We're going to include n. So for each I that we hit between 0 and n, we're going to add it into sum. And this is the expression that we'd use for that. Sum, we take what's in sum, we add I to it, and the result of that we store back into sum. That's how we accumulate each of the values through the loop. You know, I didn't say print the result. I didn't say anything like that. So this is good right here. That's enough. The key points: declare a variable, and you must initialize it to 0. If you forget to initialize it to 0, you'll have a random value for sum, and you will not get reliable results. And then for each value that you look at in your loop, add it into sum. This is kind of the foundation for a lot of programs that do linear processing. So we have to, do some kind of a linear processing. So we arrange through a sequence of values and perform operations at each step of the way. All right, let's look at 8. Write a C++ program that prints every number between 330 and 550 inclusive. Inclusive means print 330 and also print 550. Well, every number. So we're not going to do this, right? Sorry. We're not going to just type, several hundred of these lines in there. We need a loop. And so the loop is going to range between 330 and, am I still up there? Yeah. 330 and 550. So we only need one cout command.
But doesn't you just change that?
Should be that, right?
Yeah.
Good. That's inclusive. It has to include the 550. So we want to make sure that when I equals 550, that we print it. Okay, that's it right there. That's a for loop. Does anyone want to see how to do it with a while loop, or is this sufficient? Sufficient? For loop? What? While loop? Let's look at the while loop. Because actually, I might give you this and say rewrite this using a while loop. I'll probably ask that, something like that. So the while loop is very simple, actually. You can just take pieces of this. You have to initialize a variable, and then you've got a while loop, and the loop condition is right from the for loop. I mean, you can do this mechanically. You don't even need to reason through this. It's like memorizing. In calculus, memorizing a formula to compute a derivative. So it's just plugging and cranking here. And this has to be at the, remember, this is done. Where is this operation done?
Inside the braces.
Inside the braces, but where inside the braces? The very bottom.
Yeah.
So you're going to do other stuff, and at the very bottom, you're going to do that. So that means we get to put something in the middle here, and that's, of course, this one line. So that's how that works. This is the initialization. That's done once. It's not repeated in the loop. This is the loop condition. This is checked each time you're at the top of the loop. This is the end of loop statement. This is executed at the very bottom of the loop. Typically, you increment an index.
I get a question. On the for loop, does it check what's inside the parentheses every single time, or does it just do it X amount of times?
This here?
Yeah, does it check that every single time?
It checks, no, it check every time you reach the bottom of the loop.
Okay.
It'll check that.
For the for and the while.
Yeah. Actually, it checks, it does it when you first enter, when execution first arrives at the while loop or the for loop. It checks the condition.
Right.
Executes the body of the loop, the statements that are between the braces, and then you're at the bottom of the loop, and then you go back up and check the condition again.
Okay.
So you check the condition when you first enter the loop, and you check the condition each time you complete a pass through the body of the loop.
Okay.
It tells you whether to make another pass or not.
Right.
As long as the loop condition is true, you'll keep passing through the code, executing the body of the loop over and over again until the moment, the first time, the loop condition becomes false. And that's good enough to stop the whole process. You're not going to run the loop anymore. Look at this. Look at that loop. What if I put that on the quiz and said, what does this program print? It prints nothing. And I'll say, that's wrong, it didn't print nothing. No, I'm just kidding. That's kind of a joke I use with my kids, you know, and get them into. All right. So that's right. The loop condition is checked the first time you enter the loop. I was initialized to a value larger than 550, and therefore the loop condition is false right off the bat. We don't run any of the lines in the loop. Now remember, if this is a problem given the logic of the program that you're working on, you can in fact turn this into a do while loop like this. So this value for I makes the loop condition false right off the bat, but the loop condition is not checked until you pass through the loop statements once. Well, here you're going to print, what would the answer be for this one? What does this program print? It prints 830, exactly, it prints 830. But I already stated earlier that I wasn't going to cover do while. So even though we covered it twice already, I did make that promise, so this will not be on the quiz. Okay. How about exercise 9? Let's look at that one. Write a program that prompts the user to enter a number between 3 and 12 inclusive. You know, right off the bat, I know what to do without reading the rest of it, right? So I'm going to prompt the user, and you know, if I read the next sentence, maybe I'll forget about what I just read. So rather than reading forward, I'm just going to write down in my quiz paper. And this is not the way I recommend you work, okay? It's kind of the way I would do it. Because my memory is not that good, so I kind of have to manage that. So I would do enter a number between 3 and 13 inclusive.
You're going to give the next number?
Did I say, 12, sorry. Like I told you about the memory, didn't I? So, and then we're going to do cin. We better declare the number. We'll call it k. Maybe we'll call it n for number. And then cin to n. Let's pull that over this way a little. That's all right. All right, we have to print, the statement to the user, tell them what we want. Then we're going to declare the value to store the result in, the number that's inputted, and then input the number. Okay, that's the first sentence. Let's look at the next one. If the user enters a number inside 312, and that's a math expression, the square brackets means inclusive of the endpoints. If the user enters a number inside 312, the program displays good number. Otherwise, the program displays bad number. So there's the condition. If something, then we're going to say good number. Else, we're going to say bad number. Then the problem is what goes here. If the user enters a number inside 312, we say good number. So n has to be bigger than or equal to 3. And n has to be less than or equal to 12. So there's two conditions there. Is that okay? Make sense? Now look at this. This is an operation. There's two symbols, not two operations. It's one operation. This is an operation, and this is an operation. The condition, the if condition, has three operations. Which operation is done first? Or greater than or equal to 3. That one is done first. This has higher precedence than this. It has the same precedence as that. But in that case, we use left to right evaluation. So this is evaluated first. N greater than or equal to 3. Let's suppose the user enters in 5. Okay? That means n is 5. N greater than or equal to 3. What does this sub-expression that I have highlighted right there get replaced by when this is evaluated?
When you enter 5, it should say good number.
It should what?
Good number.
No, I'm not saying, I'm talking about the sub-expression. What does the sub-expression evaluate to? I'm not talking about what happens in the program.
True.
It is replaced by true. In the computer, true is a binary 1. It's replaced by binary 1. If n were 0, what would that sub-expression be replaced by? False. Binary 0. It can only be true or false. It can't be anything else. This sub-expression has a data type. It's called bool. It evaluates to a bool, which only has two states, true or false. This sub-expression will evaluate to true or false. This operator is only meaningful for the bool data type. That's why those sub-expressions have to evaluate to a bool. In the same way, the result of that AND operation, that's also true or false. So this expression here that I have highlighted right now is going to be replaced by either true or false. If it's replaced by true, we do the statements between these two braces. If this expression is replaced, if it evaluates to false, if we mentally replace it with false, then we're going to do the statements that are enclosed in the braces that follow the else keyword. So and we have one statement there, so we'll do that one. Okay, let's move to, I want to do one more thing with this one. And let's suppose we wanted to do it like this. Instead of, I want the if condition to decide that we have a bad number, and I want to put the good number in the else clause. So this doesn't work anymore. What can we do to make this work? To change what?
Change the signs. Less than or equal. No, it's less than.
What do people think about that? Give me an n that makes that true. There's no such n. That will never be true. Give me an n that's less than 3 and bigger than 12. Huh? Right, so it should be an or. If you're less than 3, you're bad. If you're bigger than 12, you're bad. If you're one or the other, you're bad. And look at the, and there's a subtle thing in here that actually programmers use that you need to be aware of if you're going to do that. And it's this expression has, they have what I think it's called short circuiting. It has a short circuit to it. This sub-expression is guaranteed to run first. And if this evaluates to true, this sub-expression is guaranteed not to run, because you don't need to run it. Once you know that this is true, there's no reason to evaluate that expression, because true or false is true, true or true is true. So it doesn't matter what's on the other side of the or operation. You're going to get true. So the left-hand side of the or operation is evaluated first. If it evaluates to true, the right-hand side of the or operation is guaranteed not to run. I think they call it short circuiting. And actually, programmers, and I don't really advocate this, but programmers may do an operation in here that has a side effect, see? And the side effect is guaranteed not to run if the first part, if the left-hand side of the or operation is a false. And you see that sometimes in scripts that system administrators write. You see that it's actually quite common in system administration. So there's some subtleties there, and it's the same thing with the and. That if this evaluates to true, then there's no reason to evaluate the second part, the right-hand side of the and operation, because you know you're going to. If the left-hand side evaluates to false, you know the whole thing is going to be false, and there's no reason to evaluate the right-hand side of the expression. And in fact, it's guaranteed not to run. That's another form of that short circuiting. It's not something that you really want to put into your code, because not everyone that's reading your code is going to notice that. But once again, in certain contexts, like in system administration scripts, you'll see this a lot. So in that context, you can expect the reader of the code to notice this effect. Okay, let's do exercise 10. And I'll just copy that over here. The above code prints odd number when the user enters an odd number. Rewrite the code so that it prints even number when the user enters an even number, and no longer prints odd number for any number. You see, this is what I had 2 quarters ago. And the problem created confusion for the students. So I added this clarification. And the problem still creates confusion for students. So I'm going to tack on another expression to help clarify even further. I don't know, there's something funny about this problem. It's just, I think it's really simple, but actually it's a little confusing. And I think the reason why is because...
It's the wording of the parentheses.
Is that it?
Yeah.
Oh, this is the part. So
yeah, that's what's confusing, because it seems like it's saying it always prints odd number no matter what number you put, but you should put and doesn't print any number at all. Or no, wait. What I'm saying is that the parentheses shouldn't say that. It doesn't print odd number at all. If that's
yeah.
what you want. Yeah.
So and doesn't print odd number at all. That's easier than no longer prints odd number for any number.
Yeah.
How about if I just say and no longer prints odd number at all? Well, you would say at all. See, is it really that much easier?
Yeah. For any number makes it seem like it's broken, and you're like, dude, it's not broken. What are you talking about? It doesn't print any odd number for any number.
It's a lot easier to program a computer, you know, than it is to program you guys.
Right.
All right. Let's take a look here. We declare an I, and we read a value into I. And then we have this this if statement. So we have to evaluate this condition, this expression, and if it's true, we will run this. Once again, this is division. Division has higher precedence than, well, it's a modulo operator, which is based on division. It has higher precedence than, what's that operator called? You know, a single equal sign is called assignment. A double equal sign is called comparison. This is a comparison. You take one side, you compare it to another side. If they're equal, then the result is true. If they're not equal, the result is false. So we take I and we divide by 2 and take the remainder. So that means we're going to get 0 or 1, right? When you divide by 2, you can either get a 0 or a 1 as a remainder. You're not going to get a 2, a 3, a 4, or 5. You won't get those remainders. So if you divide by a 2 and you get a 1, you know it's an odd number, so you print that. But we don't want it to print odd number anymore. We want it to print even number. And of course, we want to print it only for we don't want to print it for odd numbers. We want to print it for even numbers. So what do we do there? I mean, there's so
Change the 1 to a 0.
change the 1 to a 0, or what about this? We can make comparison not equal to. We can do that too, right? Those are two choices. I even saw the following someone did. Although I don't recommend this solution, but you know, this is also valid.
That's what I do. Yeah,
Oh, that was you? Okay. And what do we have there? We had, you know, that solves the problem, and it has it has the benefit of it has a record of where we came from. You know, if we go back, we look at the code, where do we come from? You could even put in good coding, you might put a note. You know, something like that. Okay, so that's it for the assignment. Huh? Make the 2 to a 3, that won't work. Because you can get a 2 as a result. So if you divide by a 3, let's suppose you take 9 and divide by 3. 9 divided by 3 gives a remainder of 0. So 6 divided by 3 gives a remainder of 0. So you get a 0, but in one case it's odd, in the other case it's even.
Oh, right.
Any other suggestions? Yeah.
When I read it, I took it as if you were putting in any number you wanted to put what it actually is, so that left the odd just added the even to it. Because
Yeah.
I gotta fix the instructions, right?
Yeah, you gotta fix it to where it says at all.
Right, because when I read it, I figured it didn't want it to.
All right, let's do it right now. I'm ready to do it. Let's do it, because I can't do this alone. I've tried this 3 quarters now. All right, let's see. The above code prints odd number when the user enters an odd number. That's okay, right?
Yeah, that's okay.
Okay, rewrote the code so that it prints even number when the user enters an even number. Can I just stop right there?
Yeah, put even number instead of odd number.
Right, because I took it as you wanted it to be either or.
Yeah, that's how I took it. So I had both, else it'll print even number. So I did both.
Rewrite the code so that it prints even number when the user enters even number.
Instead of an odd number.
But it doesn't, it sounds like it prints odd number when it's an even number, when I read the statement like that.
Rewrite the code so that it prints an even number instead of printing odd number when the user enters that number. No, don't put odd number. Just put a number.
Wow, that's getting worse. Is that what you had before?
Yeah.
That's not what he had before.
Well, yeah. I'm missing the parentheses.
And then change it, because see how it says prints an even number when the user enters an even number? Take that even out. So it says when that user enters a number.
But it has to be, if they enter 3, I don't want to print even number.
Okay.
It doesn't print anything when the user enters an odd number.
How about that?
Then, yeah, there you go. Wow, why didn't you say that like 10 minutes ago?
Because you were talking.
Agreed? Next quarter, won't have any trouble? This is from you to them. I didn't write that.
Right.
Okay.
You didn't write that.
I want to know how it's written down.
All right, I think that's it. Now, practice these assignments, put them aside, work through them again. You can even create your own variations of these questions and test yourself on these. And if you're not sure whether your answer is correct or not, what are you going to do? Compile it and run it, exactly. So that's it. And then on Monday we'll, continue, and then Wednesday we'll do the quiz.